Good
morning, everyone. Uh, Dr. Zhang, can you see me? Hear me?
Yes, I can hear you.
Okay. I'm sorry that there is something wrong with my computer, so I have to log in using another account. Good morning, everyone. I'm Dongyan Wei. Welcome back to IP 2022. It's the last day of our conference, and it's also the last keynote of our conference. In the past 2 days, the visits of our conference on the live broadcast channel have reached several thousands of record. I believe that today we will make a new record. Today, as I have mentioned, it will be our last keynote. given by Dr. Zhang Tao from AutoNavi Alibaba Group. Dr. Zhang is a senior algorithm expert in AutoNavi Alibaba Group. He received his bachelor degree and PhD degree from Tsinghua University and conducted postdoctoral research in Polytechnico in Milan. He has 15 years experience in the field of localization and navigation. Recently, he leads the group involving in the high accuracy position engine and AR engine. Supported by the high accuracy positioning engine, AMAP published the world's first land-level navigation both on phones and cars. The AR engine was applied in AMAP AR navigation and evolving rapidly to provide excellent AR experience in both outdoors and indoors. Today, he will give us a report on ARGO, augmented reality engine supporting location-based applications in the mass market. Okay, let us enjoy it. Dr. Zhang, you can share your screen.
Okay.
Thank you.
Sorry, sharing my desktop. Okay. Can you see my desktop? No?
No.
Okay.
Yes, it's okay.
Okay. Good morning, everyone. My name is Zhang Tao. I'm now with AutoNavi Corporation Alibaba Group. I'm so honored today to have the opportunity to share with you some of our recent work in AR technology. Actually, it's a combination of AR technology and the geolocalization technology. So the topic here is about ARGO. We name this, we have this name, we build this engine. It's actually an augmented reality engine supporting location-based applications in the mass market. Okay, so this is the outline. First, I will start with a review of the AR evolution, including the conception, the history, and the trend. Then the capabilities and the limitations of present AR engines will be discussed. And next, I will talk about our effort building ARGO engine based on ubiquitous signals, and also I will talk about its applications on AMAP. In the end, I will give some future prospects. So let's begin. I believe most of you should be very familiar with AR. It is very popular in recent years. And I would like to start with its conception. AR, or augmented reality, is a technology that enhances natural environmental using virtual perceptual information. So from this perception, we can learn that the primary value of AR is embodied in the following two aspects. First, AR provides the experience that combines the real and virtual world. And second, AR enables real-time interactive experience with the real world. If we refer to a similar technology, virtual reality or VR, which completely replaces the real world with a virtual one. We will find that AR has an obvious advantage for mobility users. For example, AR supports mobility users by nature, while VR users should only move in a small distance for the sake of safety. Moreover, AR can benefit mobility application users by providing valuable virtual objects. So, AR device is seen as the substitute of mobile phone. In other words, AR is considered as the next generation experience for mobile users. I think it's very exciting. And this figure shows the AR evolution in the past several decades. You can notice that this technology received great public attention when the concept was firstly proposed. And then interest wanes as implementation failed to deliver. Nevertheless, the technology continuously improved. When Apple and Google published their famous AR toolkits, ARKit and ARCore in 2017, a rapid growth of AR apps has been stimulated. Especially in recent years, the new concept metaverse brings inflated public interests on AR and VR. So if we check this chart now, we may possibly believe that we are at the start of the slope of enlightenment. This figure shows a forecast of the AR headset growth in the near future. You may notice the dramatic growth in the year 2022. Yes, it is this year exactly. So I think we will be expecting this. And more importantly, the consumer market is considered to lead the growth, which is very different from today's AR market. We know that in today's AR market, Google AR Glass will be used just in the enterprise market. So what is the AR market like today? What do you think is the most popular AR use case in today's consumer market? I think the answer may be the filters and lenses. You should be very familiar with these functions. When you make a short video or have a video call on Snapchat or TikTok, you use a function because they are fun. Yes, it's very fun, but I have to see they're only for fun. So if you may recall what we said in the first slide, AR is considered as the next generation experience for mobile users. You should realize what a huge market space exists. Here we illustrate some applications that may be changed or enhanced by AR. They should include like social communication, navigation, education, game, fitness, retail, tourism, and more. For example, navigation should be much more intuitive with indicating signs overlaid on real world. And even more, these virtual signs can give user easy access to actual information like historical sites or top restaurants, or even someone you want to meet. In short, AR application in the future should be and are possible to be much more useful, not only for fun. So the next question is, how do we support these AR applications? The answer is AR engine. Next, we will have a glance at the present AR engines. Typically, there are two categories of AR engines. The first is developed by mobile phone maker and supports only specific phone brand. The famous AR kit is in this category. Since they can make better use of their hardware, they possibly have better performance. The other category of AR engines is built to support various phone brands, like AR Core developed by Google. And also in this category, we can see Snap AR, Spark AR, Sense AR, or Easy AR in China. So here we take AR Kit as an example to show the engine's capabilities. As you can see, AR Kit provides multiple methods to understand and track the real world. The methods are different according to different tracking tasks. For example, if you want to make AR face lenses, you should be interested on the face tracking method. But as we have mentioned before, we put eyes on mobility users who should be benefited by location-based AR applications. So we can find the two key methods to support location-based applications are word tracking and GEO tracking. The word tracking usually use visual initial odometry or VIO to achieve precise 6DOF tracking in the camera frame. The GEO tracking applies end-to-end visual positioning, or Google called it VPS, to achieve precise position and orientation in the word frame. The word tracking method was supported by the first ARKit edition, since it actually forms the basis for almost all AR applications, while the ARGO tracking method was released in 2020 and support only 5 cities in the US. And after that, Apple continuously expanded its supporting regions in the past 3 years. However, the coverage is still limited. We can see it's only just 60 cities all around the world. And a similar method in AR Core was also released by Google this year. Benefited by Google's Street View images, the method has a much wider coverage than ARKit. Actually, it says this method can cover where Google Street Map covers. So that maybe it maybe dozens of countries. But the bad news is it's still unavailable in China. And apart from ARKit and AR Core, no other engines has a similar geolocation tracking method. In this page, we summarize the major limitations of present AR engines in supporting location-based AR applications. As we can imagine, geolocation tracking should be the essential feature for location-based AR, but only limited outdoor scenarios are supported, let alone the indoor scenarios. The limited scene coverage will obviously reduce the utility of a location-based app like navigation. And another problem is that present AR engine can support only limited mobile devices, which make it difficult to expand its users. And the last but not the least problem is a high CPU load. It will cause the mobile device heating up and draining battery. And as a result, mobile users don't like to use AR for a long time. That is the problem we face today. So considering all these limitations, we built a new AR engine, ARGEO, to fill the gaps in location-based AR experience. The term ARGEO is a combination of AR and geolocation. To achieve satisfied AR experience, the engine should be capable of precise and robust real-world tracking. And in addition, it should provide continuously reliable location and pose in the geographic world frame. Also, we want it adaptable for the majority of mobile devices in the mass market and has relatively low computational cost. In one word, we aim to build ARGEO as a lightweight AR engine focusing on location-based AR applications. This page shows the whole architecture of the ARGEO engine. As you can see, it has two parts. The inner part is the AR tracking core, where the camera and IMU are integrated to fulfill the real-world tracking task. And in the outer part, we make use of ubiquitous signals like GNSS, Wi-Fi, Bluetooth, geomagnetic, and electric to guarantee the continuous geolocation and pose tracking. We developed two methods, the tightly and loosely coupled methods, to fuse camera and IMU in the AR tracking core. The tightly coupled method can provide higher precision while require accurate synchronization and sensor parameters. So it only applied on some certified devices. For the majority of varied devices, we developed the loosely coupled method, where two independent tracking precises, the visual odometry and pedestrian depth reckoning, run parallelly and then integrated into the final pose. This method do not need accurate synchronization and is also robust to IMU parameters, so it can be easily applied to various devices. Besides, it also reduces computation cost since the estimation problem scales are reduced. One possible problem is that the tracking position may be lower than the tightly coupled method. We make great efforts on improving the VO availability and better integrating with PDR estimated scales to achieve a competitive position. As we have mentioned, ubiquitous signals are fused in the outer level to achieve geolocation tracking. Two major audio signals are GNSS and vision. GNSS has been widely used, but suffers from problems like signal loss, multipass, and electric. We improve the GNSS position using map edit positioning. Since we have rich surveying data from satellite images to road vehicle collected LiDAR point clouds and images, we can build 3D or at least 2.5D map for most areas in China, and hereby enhance the GNSS positioning. Besides, we also built a visual positioning system based on our road vehicle collected images for those applications requiring higher pose accuracy. As to the indoor scenarios, visual positioning can also be applied. Our system has supported hundreds of buildings with different types, such as shopping malls, train stations, and airports. But the problem is the vision data collection process is not so convenient and costs a lot, let alone the privacy risk. So we also include other environmental signals in our system, like Wi-Fi, Bluetooth, and geomagnetic field. We use Wi-Fi fingerprint positioning, and we can achieve 5 to 10 meter accuracy in most indoor places. So you know the accuracy seems not high enough, but it can serve as a good initial position substitute. And then this position accuracy can quickly converge to about 1 meter level using geomagnetic matching. Besides, acoustic and visible light signals also have potential to accurate indoor positioning, and we will include these signals in the near future. Finally, we fuse the relative poses produced by AR tracking core and global poses from map-edit GNSS, VPS, and geometric matching in a graph optimization framework. The graph optimization is shown here. This page shows the main features we achieved by ARGEO. The engine can be applied in most outdoor scenarios and hundreds of indoor places like shopping malls, airports, and train stations, and the buildings are still expanded quickly. The engine also has good adaptability to various mobile devices, including most iOS and more than 80% Android devices. By the way, the number is still increasing and is supposed to exceed 90% recently. The engine also has a relatively low CPU load, according to our tests in the real-world AR application. Next, I will talk about the ARGEO applications on AMAP. And before that, I would like to give a brief introduction to AMAP. AMAP is a top Chinese mobility app. Every day, tens of millions of active users enjoy location-based services on AMAP. For example, we provide navigation services covering various transportation types like cars, bus, metro, bicycle, pedestrian, train, and electric. And we also provide real-time information like the arrival time of nearest bus. So you know it might be very important and very useful for you. Besides, people can enjoy many different types of life services on AMAP. For example, you can book a ride, a hotel room, or an attraction ticket. You can also get coupons of a restaurant or a shopping mall. The first ARGEO application on AMAP is the AR navigation for pedestrian. It was released in 2021, and updated in the following versions to support more than 95% mobile phones in the market. And one remarkable feature in this application is a highly accurate heading, which is very important for pedestrians to find their way. And it is achieved by fusing visual information when the phone canvas is interfered. So we can see a video, introduction video of this AR navigation for pedestrian. Okay, and I recommend you to try this function. And if you have any problem or questions, you may feedback to me. And another application I will introduce you is an AR assisted pickup. When you book a ride in a shopping mall or a train station, you can use this function and follow the virtual instructions to get the pickup point easily. To fulfill this function, ARGEO should achieve at least centimeter level positioning accuracy and 6DoF tracking indoors. We are continuously expanding supported buildings and expecting more users can enjoy this function. And here I would like to repeat our goal of building the ARGEO engine. We aim to build a lightweight AR engine focusing on location-based applications. To achieve this goal, we will increase the scene coverage, especially the indoor places like stations and underground lots. We will also support more devices, as we have mentioned, at least 90% and more in the near future. The computation load will be further reduced using optimized algorithm and programming. The precision and robustness will be continuously polished in all specified scenarios. You know, it's very detailed work. At the same time, we will expand the AR applications on AMAP and leverage the user data and feedback to achieve all these improvements. And in the future, we expect ARGEO to be an out-of-the-box engine that can support more applications outside AMAP. So finally, the vision for ARGEO is to make AR useful, affordable, and easy to apply. Thank you. So this is my talk.
Okay, thank you, Dr. Zhang. Thank you for your excellent presentation. I think in China, we use navigation software almost every day, such as Google Map. So I have actually experienced many experience. I don't know whether Google provide the same service abroad. So I don't know whether the foreign participants have experienced them. Is there any questions from the audience? So I have a question. As you have mentioned, for pedestrian navigation, heading of direction is very important.
Yes.
What technologies do you use to provide accurate direction for pedestrian?
Yes, that's a very big problem, and I think it's very essential for our navigation users. Generally, we use magnetic to find the heading, but it is very easy to be interfered by like buildings or other electrical devices. The way is to find another input to get a heading. I think the answer maybe is if we can find a way to use the vision information to give us this heading. And if you use vision, you have many. You have also have different methods to get this heading. For example, if you can build a vision map, you can just relocation your 3D UF pose in this vision map. That's one way, but I think it's maybe cost a lot. Yes. But in some place it's very important, like indoors, we can do this thing. Indoors, we can build this map and location yourself in this vision map and get very, very accurate heading. But for most outdoor scenarios, I think we can make use of other, in AutoNavi, we use our digital map as an input. For example, if you know where you go in this road and you know the heading of this, you know the road direction, and you know where is the direction of your phone compared to this road, you can do something to correct your heading. So that is a more generate method to do this thing. But I think there are other ways. I think the most important thing is you can find an input.
So you don't use a magnetometer, a compass?
Compass, yes, we use it. We just use integrated method, not just one method.
Okay.
Yes.
And you said AR consumes a lot of resources, computing resources.
Yes.
So in your system, is computing done in cloud or just on the mobile phone?
I think that the tasks will be different. Maybe some task, for example, relocalization precise with vision map can be computed in the cloud. But if you are doing something like odometry, VO or VIO odometry or PDR, that will just you can just compute it in your device. So we should use different device in your client or the cloud to do different things and then fuse them.
Okay. Any questions from the audience? The volunteers, can you check whether is there any question from the live broadcast platform? Okay, it seems there's no problem, no
Okay.
question.
Okay.
So thank you again, Dr. Zhang, for your excellent report about indoor navigation. So let's move to the next part of today's conference. It will be the parallel sessions in room A, room B, and room C. Okay, that's all for this session.